In this section, we're going to talk about oxidation-reduction reactions. Oxidation and reduction reactions are another type of reaction that takes place in an aqueous solution. They are reactions that involve a transfer of electrons from one substance to another. The term oxidation and reduction reactions comes about because the first reactions of this type that were studied dealt with oxygen. So that's where the term oxidation comes from. So let's start talking about what these individual parts are. Oxidation is the loss of electrons from an atom. We talked earlier about metals, and we said that metals tend to lose electrons when they react to form a positive ion. So oxidation is the loss of this electrons. Now, when things are oxidized, the item that is oxidized or has lost electrons we call the reducing agent, because it is giving its electron to another item, thereby causing its charge to be lowered or reduced. So the item that is oxidized is the reducing agent. It's a little bit confusing, but sort of just remember that they're opposites. The term reduction involves the gain of electrons. Nonmetals tend to be reduced. Now this is the one that gets most students confused, because when you think of something being reduced, you think of losing something. But remember what it is. It's not that the item is being reduced, it's the charge is being reduced. So when you gain an electron, you're gaining a negative particle, therefore lowering the charge by 1. So reduction involves the gain of electrons. Again, just like before, an item that is being reduced is called the oxidizing agent. So generally speaking, nonmetals, which oxygen is one of them, tends to be what is called the oxidizing agents. Metals tend to be reducing agents. They tend to lower or reduce by giving away electrons to another element. Now, because the law of conservation of mass says that matter can be neither created nor destroyed, it is impossible to have oxidation without reduction. If something is being oxidized, something must be reduced, because oxidation is the loss of an electron, reduction is the gain. In order for the law of conservation of mass to be maintained, if an electron is being lost, it has to be gained somewhere else. Now, two little mnemonic devices that we use to remember one of these things is that the first one is oil rig. The expression oil rig stands for oxidation involves loss, reduction involves gain. And then the second one is Leo says Gur, meaning Leo the lion, like the Leo symbol. And that stands for loss of electrons, oxidation, gain electrons, reduction. Either one of these are ones that I've given students in the past and seem to be the most helpful. If you can think of one yourself, obviously you may feel free to do so. To keep track of the electrons that are lost or gained in an oxidation-reduction reaction, one of the most useful things to do is assign an oxidation number. And an oxidation number is simply a number that describes how many electrons are typically lost or gained by that element in the reaction or in an reaction to form a compound, or when the compound is formed. The following set of rules we're going to use are useful in determining oxidation numbers, and there's a set of rules, and you can follow along with your notes. Rule number 1 says for an atom in elemental form, the oxidation number is always 0. We talked about the fact that if you see an element existing by itself, it's going to have no oxidation because elements are neutral overall in charge. They have no charge to them. Hydrogen, for example, is listed as H2. We know that H2 is the form that hydrogen exists in because it is a diatomic molecule. In a chemical reaction, if I see H2 written, hydrogen in that case has a 0 oxidation number. Some other examples are if I just see a symbol Na, just plain for sodium metal. By itself, without any charge shown, it will have a 0 oxidation state. If I see another element in a molecular form, like S8, it still is going to have a charge or oxidation of 0 because that is its natural elemental form. So again, rule number 1, atoms in elemental form are 0 oxidation. Rule number 2 says for monatomic ions, the oxidation number equals the number of the charge. So if I see a charge given, then whatever the charge given is the oxidation state. So if I see Na 1 minus or 1 plus, should say, it's going to have a +1 oxidation state. If I see Mg plus 2, it means it's going to have a +2 oxidation state. If I see Cl minus 1, it has a -1 oxidation number. Rule number 3 refers to nonmetals, and nonmetals are the ones that can get a little bit tricky. Metals are pretty much always the same, and the numbers we've looked at for charge are the oxidation numbers. But for nonmetals, oxidation numbers can be all over the place. Generally speaking, they're negative, but they can be positive in certain situations. Let's start with looking at oxygen. The oxidation number of oxygen usually is -2 in both ionic and molecular compounds. The major exception is when we have peroxides, and peroxide is one of your polyatomic ions you had to know, which is O2 with a -2 charge. Anytime you see O2 in a formula, each oxygen in that case is going to be -1 instead of -2 oxidation state. So in the compound hydrogen peroxide, H2O2, each oxygen is -1, total of -2 altogether. Hydrogen is another one that can be positive and negative. Generally speaking, the oxidation number of hydrogen is +1 when it's attached to nonmetals, -1 when it's attached to a metal. Easier spoken, if hydrogen comes first in the formula, such as an acid, then hydrogen will be a +1 oxidation state. If it comes second in the formula, then it will be a -1 oxidation state. The halogens are also a set of family that can be positive and negative in different situations. Fluorine is always -1 in all compounds. Under no circumstances will be anything other than -1. The other halogens generally tend to have a -1 oxidation state in most binary compounds. Remember, a binary compound is a compound with an element plus that other element, so 2 elements. So for example, in calcium chloride, chlorine has a -1 because it's a binary compound. Now, when do chlorines and iodines and bromines not have a -1 or have a positive oxidation? It's when they are combined with oxygen, as in oxyanions, so the polyatomic ions. Then they will have a positive oxidation state. So for example, if I have chlorate, ClO3 -1, in this case, chlorine is going to have a positive oxidation state. And what number it would have, we will figure out here in a second. Rule number 4 deals with figuring out the charge on some of these unknown things. The sum of all oxidation numbers in an atom or in a molecule have to add up to 0. Just like when we were doing ionic compounds, we said that in order to figure out the total charge of the metal sometimes, we had to figure out the charge of the nonmetal. In these cases, the sum of all things have to add to 0. If I have a polyatomic ion or a particle with a charge, then the sum of the oxidation numbers must add to the charge of that particle. Now let's look, for example, here how we would assign some oxidation numbers to some compounds or elements in compounds. In our first example, we have lithium and oxygen. In this case, lithium, whatever charge it has in the metal originally we have will be its oxidation. So lithium, since it's in the first family, is going to have a +1 oxidation state. Oxygen, we just learned, will always have a -2 unless it's peroxide. This is not peroxide because there's no O2, so oxygen is -2. In our next example, H is +1 because it's written first. When hydrogen is written in the front and acid is +1. Oxygen is -2. So a total of -6 because I have 3 oxygens. To figure out the nitrogen, we have to look at adding up to 0. So hydrogen's +1, all the oxygens add up to -6, so nitrogen has to add up to making the whole thing 0. So +1 -6 plus nitrogen has to equal 0. Therefore, nitrogen in this case would have a +5 oxidation state. In our next example, we look at the particle, and it's different than the others we've seen so far because it has a charge attached to it. It has a -2. Now, in this particle, all the things must add to that charge. Oxygen, we know, is -2. Therefore, it's a total of -14. Now, chromium can have multiple charges. It can be 3, it can be 6, it can be 2. Most commonly, it's 3. So in this case, let's figure out what it is. -4 plus 2 chromiums has to equal -2 in this case because the charge of the particle is -2. So if we have 2 chromiums, do a little mathematical manipulation, equals, subtract 14 from both sides, or add 14 from both sides, we get 12. So chromium, each one has to equal a +6 oxidation. In PF3, our example is fluorine is -1. We said fluorine is -1 in all cases, giving us a total of -3. Therefore, phosphorus must be +3. In a permanganate ion, oxygen is -2. I have 4 of those for a total of -8. So -8 plus manganese has to equal -1. By little algebraic expression, we can figure out that manganese is +7. Now, why is this useful? It's useful to us because in a chemical reaction, then, this will help us figure out what is being oxidized and what is being reduced. If I have a reaction such as the following. In this reaction, we have to check to see if this is an oxidation-reduction reaction. Generally speaking, there are 3 types of reactions that will be oxidation reduction: combination, single displacement, and combustion. Combination, single displacement, and combustion reactions, generally speaking, tend to be oxidation and reduction in nature. Now, how can you tell what's being oxidized and what's being reduced? Now, we've said that, again, most of the time that oxidation is the metal, reduction is the non-metal, but that isn't always the case. The way we tell is simply, to be sure, is we start before and after. Before the reaction and after the reaction, we figure out oxidation states. Before the reaction, magnesium is by itself, which means it has a 0 oxidation. Oxygen is in its natural state, so therefore it has a 0 oxidation as well. After the reaction, they are joined together now. And so when magnesium and oxygen are part of a compound, oxygen is -2, and magnesium is +2 as part of the compound. Magnesium has gone from a 0 oxidation state to a +2 oxidation state. The only way things can become more positive is to have lost electrons. Therefore, since magnesium has lost electrons, it has been oxidized. So we say that magnesium is oxidized. Oxygen went from a 0 charge to a -2 charge. The only way you can become more negative is to have gained electrons. So gaining electrons is reduction. So oxygen has been reduced. So in this case, since magnesium is oxidized, it is the reducing agent. And since oxygen is reduced, it is the oxidizing agent. In the next coming section, we're going to look at how you use this then to tell if some reactions actually do or do not occur. Again, just like in double displacement we talked about in Chapter 3, we just assume they happen and wrote the equation. But earlier on in precipitation reactions, we learned that that's not always the case. Sometimes you'll have products form that aren't solid, therefore a reaction does not occur. In the next section, we're going to look at that, what happens in a single replacement. So we just talked about determining oxidation number and how you tell what's being oxidized, what's being reduced. And we talked briefly about the combination, combustion, decomposition reactions, and single replacement reactions, generally being the ones that are always redox. Single replacement reactions are the ones that we see most frequently. Combination, combustion, and decomposition are generally redox. You know they're going to be. Single replacement reactions are redox when they happen, but they don't always occur. And we can use redox to figure out whether or not a reaction is or is not going to actually occur. In general, metals and nonmetals tend to be oxidized or reduced by either salts or acids. One of those 2 things will lead to oxidation or reduction. How can you tell? The way we can tell is simply using a chart called the activity series. And the activity series is provided here in your notes and in your book. And in your book, it's on page 143. The activity series basically lists the elements or the metals in order of activity as from top to bottom. The ones on the top are the easiest to oxidize. The ones on the bottom are the hardest to oxidize or hardly ever get oxidized. Now the way we tell is we simply, to use the activity series, I have 3 examples of reactions here, and we're going to use the activity series to determine whether or not these reactions happen. And if they do happen, we're going to figure out what's been oxidized, what's been reduced in the reaction. In our first example, we see zinc is reacting with hydrochloric acid. When I put zinc and hydrochloric acid, we, in Chapter 3, made an assumption that this reaction would occur. And we said that zinc would go with chlorine, hydrogen would go off by itself in a single replacement reaction. From this point forward, we can't always make that assumption. We have to look at our activity series to tell, will this reaction occur or not? The way you tell is as follows. On the activity series, you first find the element that is by itself, zinc. So on my activity series, I find zinc, and zinc is located right there. You then find the cation of the acid or salt that's reacting with the zinc. In this case, the cation is hydrogen. Hydrogen is right here on the list. The rule says if the cation is below the element on the list, reaction does occur. If the cation falls above the single element on the list, no reaction will occur. So in this case, since hydrogen is below zinc, hydrogen will oxidize zinc. Therefore, our reaction will occur, and we'll get zinc solid joining up with the chlorine in a single replacement to form zinc chloride, and that will become aqueous. And if you don't know how to tell that it's aqueous or not, look at your solubility rules. It will be aqueous, and then hydrogen will go off by itself, and hydrogen by itself naturally occurs as a gas in solution, so it will bubble out. So that reaction will occur. Let's look at another example. Again, to figure out whether or not this reaction happens, we find the element by itself. We find silver. Silver falls right here on the list. We then find the cation of the salt in this case, because zinc nitrate is our salt, and we find that zinc is up here. In this case, since the cation is above the single element, we see that no reaction will occur. So we don't write a product, we simply write NR, no reaction. In our last example, we do the same thing. We take lead, we find lead on our list. Lead falls right there. We then find the cation of the acid or salt. In this case, again, we have a salt because it's CuCl2, and the cation is copper. It falls right there. Since copper is below the lead, copper will oxidize the lead, and our reaction will proceed, and we'll get Pb. Now, since we don't know the charge of Pb, in this case, because it's going from a neutral element to a charge, we will use the most common charge, which is +2, and we'll get PbCl2 formed. And PbCl2 is going to be a solid, producing out of that. And then we will also get copper metal formed out of that as well. So we're going to get two solids being produced out of those solutions, and they'll both precipitate out. Now, the second part of the question is what's being oxidized, what's being reduced? Well, obviously, in the second reaction, nothing is oxidized, nothing is reduced because the reaction does not occur. In our first example, zinc was 0 on this side, hydrogen was +1, chlorine was -1. In the product side, hydrogen is now 0, zinc is +2, and chlorine is still -1 each. It's -2 total, but each one is still -1. So chlorine has neither been oxidized nor reduced because it has the same oxidation number before and after. Zinc went from 0 to +2. So in order to become more positive, you have to have lost electrons, so zinc was oxidized. And hydrogen went from +1 to 0, so hydrogen was reduced. In our last example, Pb went from 0, copper was +2, chlorine was -1. On the other side, lead is +2, chlorine is still -1, and copper is now 0. Lead went from 0 to +2, so lead was oxidized. Copper went from +2 to 0, so copper was reduced. And chlorine didn't do either. Now, it's important to point out here in this last example that we said that metals tend to be oxidized, non-metals tend to be reduced. In other words, there's tend, not are. Because in this example, we can see that a metal is oxidized by another metal. All right, so copper is oxidizing lead, so lead is being oxidized and copper is being reduced. So at the same time, you have both things happening. Whereas in the first example, metal is oxidized and a non-metal was being reduced. All right, so this wraps up section 4.4, oxidation reduction. And you now have some activities to do to practice them.